Okay, good morning. I thought I would start the lecture by showing a few slides, which will remind you what I did yesterday, and then I'll proceed with some Blackboard calculations. So one somewhat non-standard thing that I introduced is the notion of a stranded graph, or where there are loops of different colors. So a simple case where this arises is this real matrix model with ON cross ON symmetry. And I wrote the interaction in this form with indices, but you can also rewrite it in the matrix form, like trace phi transpose, phi transpose. And then it's completely clear that this symmetry, so first of all, this is what you would call single trace interaction. Single trace, right? Because obviously there is one trace, right? There is also double trace, as I mentioned. Double trace, which here you would write as trace phi transpose all squared, right? And both are allowed by the symmetry. And then you see that the symmetry obviously works if I send phi to R1 phi R2 transpose and just plug this in here. You'll see that with the requirement that R1 and R2 are orthogonal matrices, you will get that this is invariant. Okay, so what I was talking about was mainly the graph interpretation, and you can write this vertex in this. First of all, you can write the propagator in the scalar double line notation, and then the vertex looks like this, which I try to draw on the Blackboard, but it's always nice to see prettier pictures. So this is what it looks like. And then there are only planar graphs surviving in the large N limit. So let me just show you a chunk of a planar graph. So if I keep this Gn fixed, then the graphs are going to look like this, okay? And you see that there are alternating loops, like there will be green loops, and then there will be red loops, right? So they alternate. And then it's very useful to think in terms of the dual lattice, right? The dual lattice is where you put a dot in the center of each of these index loops and then connect them. So because the interaction vertex is quartic, right? At each interaction vertex looks like this, right? It's the same as what I drew last time. So this means that that the dual lattice just consists of you can think of them as squares. Since a priori we don't assign lengths to these, you can think of each of these as actually a square. And then, so this is a standard way to think about it. Then you think about each of these angles as 90 degrees, right? So if each of these is a square, then you see that curvature is concentrated at these vertices, right? So if there is if four squares meet at a point, for example, what you have here, then there is no curvature delta function, right? Because the angles add up to 360 degrees. But if more squares meet at a point, then you have negative curvature, and if there are fewer, then you have positive curvature. Okay, so this is a standard way to associate these type of discretized surfaces with two-dimensional geometry of some kind. And the only unusual thing is that these squares actually have two types of vertices. One vertex can go in the center of a red loop, and another vertex can go in the center of a green loop. So when you glue these squares, you can only glue red to red and green to green. So not all possible orientations are allowed when you glue them, right? You cannot glue, by definition, a red vertex to a green vertex. So it gives you some reduction in how many possibilities you have. But for matrices, it's actually not very significant. And this type of matrix model also is associated with two-dimensional quantum gravity, just like the uncolored model, where you have only UN gauge group. And so the one where you don't get colored vertices is, as I mentioned, is, for example, this just SUN, where you have only one symmetry, SUN, and you take the matrices to be adjoints of SUN. Then there is no notion of coloring, but there is notion of orientation, because each propagator can be drawn with these arrows. So in this type of model, if you write down log z divided by n squared, you will have basically f0 of lambda plus 1 over n squared f1 of lambda plus dot dot dot, right? So the suppression is only in powers of 1 over n squared. You don't allow 1 over n. And this is a sign of orientability of the surface. But for this, and in this case, you can even, for example, allow these triangulated surfaces. So there are these, instead of double lines, I drew here dashed lines. But you see that the dual lattice here is made of triangles. So this was explored a lot, as I mentioned, in the late 80s and early 90s. And you could look at, for example, my Trieste lectures from 91, or there is a very extensive review by Moore and Ginsparg. It's almost a book where they review also matrix models, just matrix integrals, not matrix quantum mechanics, but just matrix integrals, which is the most elementary thing you can do. And so when you sum over two-dimensional geometry, you get the so-called Liouville theory. So the idea is that the summation over graphs gives you a kind of path integral for 2D quantum gravity, where you have integral of, say, the integral over two-dimensional matrix, e to the minus s. And then when you adopt the conformal gauge, that g mu nu is equal to delta mu nu e to the phi. This is what people often call Liouville field. And then you get some effective theory, which is like an interacting theory of the scalar field. So this is not the main topic of my lectures, but you can certainly read about it in various sources. Okay, so this was largely the motivation. It was like a toy model for string theory, because you can think of these random surfaces as world sheets of a string, which is very low-dimensional model of the string. This Liouville field provides you kind of one dimension, and if you have matrix quantum mechanics, then this Euclidean time x provides you with another dimension. That's why my review was called two-dimensional string theory. So now, so I want to recoup a little bit the really new stuff that I'm talking about here, which is the tensor models, right? So for the tensor models, the idea of coloring is very similar. So now you have a rank 3 tensor, phi ABC, and the two-point function just has product of these delta functions. So you can denote it by this triply colored stranded graph. Right. You can also think of just the overall line as a cable, and inside this cable there are 3 wires, right, of 3 different colors. And then, as I mentioned, there is a very special tetrahedral interaction that you can have, which preserves ON cross ON cross ON symmetry, which can be drawn like this. It's like taking the matrix interaction and then putting in a blue line, 2 blue lines in the middle so that they cross. They cross one under the other. Okay, and in terms of the index contraction, it looks like this. So this is one of 3 possible interactions that you can write down. There are also the interactions where the blue lines kind of miss each other and go like this. That one is, does not give us by itself a melonic limit. It turns out that this one is what's really important for giving us the melonic limit. Okay, so as I mentioned, you can think of, so for example, here is the very basic graph that I drew. So if I start expanding log z in vacuum graphs, this is the simplest two-loop graph that you can write down, right? I drew it yesterday on several occasions. And then, as I explained, it's important from the analysis of the two-point function, it's important to keep this lambda fixed in the large N limit. Okay, then when you draw this, this graph in terms of the stranded notation, you see that there are two blue index loops, two red index loops, and two green index loops. So you get like g squared times n to the 6, because each index contraction gives us a power of n. Now, in this case, there are n cubed degrees of freedom, right? So, for example, just the number of degrees of freedom in phi is exactly n cubed. So that's why you want to take this n cube out, right? Just like, for example, for the matrix, I took this n squared out, and then I obtained the finite f0 of lambda and plus 1 over n corrections. Here I have to take n cube out, and then you see that this graph indeed gives us something that after you take, so for tensor model, for tensor you get this log z over n cube, okay, will give us some f0, we can call it f0 tensor of lambda, plus some 1 over n corrections. In fact, these corrections are of order 1 over root n in this case. It's a very small suppression, it turns out, times some, we can call it f1 half of lambda and so on. These are basically pretty hard, so I will not discuss them. But I will show how in just the model of tensor integral you can extract this leading quantity. Actually, it's possible for the d equals 0 model. Okay, and then, so what do higher melonic graphs look like? Well, you can, again, insert this melon in each of the propagators. You can have just sort of one overall propagator with more and more melon insertions here. Yeah, people often ask where are the melons and why are they called melons. I'll have a funny slide about this. Yeah, I mean, they start looking more like melons if you put in more stripes here. But basically, these are, before they were called melons, there were some old papers where people called them other things, like blobs, for example. But okay, so this one, if you draw the stranded graphs, which allow you to, now I want to stress that I don't mean that only this type of connection is possible. There are also pieces in this diagram which have fewer powers of n. They contribute to this other stuff, to suppressed pieces. I'm just trying to draw the maximum number of loops, right? The way of stranding this graph with the maximum number of loops. So similarly here, if you draw the graph with the stranded number of loops, yeah, in a sense, this is the basic melon insertion, right? So here you see that you insert in the propagator something where you have this additional blue loop, right, an additional green loop, and an additional red loop. So you can keep inserting this melon inside the propagator, and this will keep giving you additional powers of n cubed every time you see g squared. That's why this one also works. So you get, again, n cubed you divide out, and then you get lambda to the 4. And then the idea would be to try to, at each order, only include this leading large N contribution and see how, if we can sum this up. Okay, so this is in a nutshell the basic news. Right. So why were people working on this originally, and why? You can always ask why. So I think the big impetus was actually this matrix model stuff. Right, this was a big success. Here you can solve the model, and this clearly teaches us something about low-dimensional models of string theory. It also may have just some statistical mechanics applications, like sometimes you want to sum over surfaces where the triangles are not in a regular pattern, but they're connected in arbitrary patterns. Okay, so this was, the basic ideas for this were from the 80s. And then in the early 90s, people actually started saying, well, if a two-index tensor can help us understand two-dimensional quantum gravity, and there were really big successes in that. Like, for example, you can, from this Liouville calculation, determine some quantities, and they match in a certain limit. So in the matrix model, you want to take the limit where the number of these elementary plaquettes become very large. When you take that limit, you get results in excellent agreement with Liouville theory. So it was regarded as a big success. And then people started wondering, can we understand three-dimensional Euclidean quantum geometry by going to rank 3 tensors? And the basic idea you can see is geometrical. It's related to this. That's why we call this the tetrahedral graph. It's actually, you can think of this as a kind of view of tetrahedron from the side. And then when you do perturbation theory, you just start gluing tetrahedra. And so you get some kind of 3 geometry. And that was the basic idea in these 3 papers from 1991, 1992. And the original models, maybe this one even had some semblance of this tetrahedral vertex, although it's not totally clear to me. They were a bit sketchy, these papers. They all worked with the case of what we would not call the colored graph. There was just more like this story, like either one SUN group or basically one ON group. And they didn't get very far. They basically decided that the large N limit is just too hard to analyze. They did not get this idea of scaling G as n to the -3/2, for example. That was discovered much later in the work by these people. And then in the very first papers are also like, they're phrased in the context of something called group field theory that Bulatov invented in '92. They're just some, if you read them, you will not realize right away that they're dealing with tensor models. Tensor models are a bit simpler. But then today I will review a paper from, I think, 2011 by Bonzom, Gorau, Riello, and Rivasseau, which is written very much in the language similar to the matrix model. And actually, that's where the term melons, I think, for the first time appeared. Okay, so why is this three-dimensional geometry? Well, you can start thinking of each of these vertices as a kind of, again, we go to the dual lattice, and then we can think of the dual lattice as made of tetrahedra, similar to how the dual lattice and the other thing was made out of squares, for example. And so you can draw these tetrahedra, and they're glued in certain orientations with each other. Like, they're glued along triangles, and blue to blue, edge green to green, red to red. So here you glue them along this edge, and then you glue edges like this. So these black lines show how the edges are glued. And these are also can be viewed as some types of gluings. So you get some notion of three-dimensional geometry, but as we'll see, it's not a very satisfactory set of three-dimensional geometries. Unlike in the 2D case, where there is evidence you're picking up really good set of geometries here, it seems like you're only getting some very degenerate geometries. So far, this approach has not taught us much about three-dimensional quantum gravity, but it does reveal this new type of large N limit where a very peculiar set of these graphs survive. And these are these graphs I mentioned from last time. Right, so this was realized already in a few years ago. So these are the first two Mellon graphs, and then you can start basically iterating these insertions, and these are all Mellon graphs up to a certain order, okay? One thing that you can realize is that these Mellon graphs also have a kind of linear structure to them. Remember, like when we were dealing with vector models, they all have this linear bubble structure. You just build linear bubbles. All the Mellonic graphs can be drawn essentially like this. You just have these two propagators. You have two Mellons on the ends. Okay. And here you have these insertions. So it may not be immediately obvious to you why these are all Mellons, but these are a bit like Mellons inside Mellons. If you can, when you think about them, they can also be drawn like this, for example. Like if you start with a basic Mellon like this, right? And then you can put in Mellon within this Mellon, and then Mellon with this Mellon, Mellon with this Mellon, and so on. Right, so you can, on the one hand, just think about Mellonic insertions in these internal propagator lines, or you can think of it as a ladder. So that's one thing you realize is that Mellonic graphs are ladder-like. Ladders. And ladders, we tend to know how to sum, right? They're summable. It's somewhat more complicated than the ladders, the chains of bubbles you get for vector models, but it's still doable. So in the end, it's a much, much simpler theory than you could have expected to get. And actually, I'll show evidence that this gives the so-called branched polymer phase of the geometry, which is only a tiny subclass of three-dimensional geometries. So I call them Mellons. Maybe watermelon is a better name. Right? In fact, you can generalize the model with rank 3 to rank q minus 1. And then it turns out that you need, in the simplest incarnation, you need the phi to the q interaction. So for example, in this model, 1, 2, 3, 4, 5, 6. This is phi to the 8 model. So now this is starting to look more like a watermelon. And in some earlier work, it was called blobs. And this class of diagrams dates back to 1964. In a paper that was actually attempting to understand three-dimensional Ising model of all things. And they had this wild idea to only essentially sum these type of graphs, which in the end, of course, is not correct, but they stumbled in some sense on the same Schwinger-Dyson equation that I'll show at the end of my lectures. Okay. Now, just to stress, there are lots of non-Mellonic graphs. Most graphs will not be Mellonic, and one can check this rather explicitly. For example, in vacuum 5-4 theory, this is a graph of order G cubed, and when you try to draw the maximal number of stranded loops, you see that there will only be 6 of them while there is G cube scaling. So this graph actually is suppressed by n to the 3/2 relative to, so there are these fractional powers here. It's suppressed by n to the 3/2 relative to the Milonic graphs. There are also some snail graphs which I showed and will show again, which only are suppressed by 1/√n, not by 1/n to the 3/2. And because of this funny n to the 3/2 scaling, you can easily see that there is no way that any graph with an odd number of vertices can pick up n cube scaling. It will have to be a fractional power, right? Like n to the 3 minus 1/2. So no graph with an odd number of vertices is Milonic. That's why in the leading large n limit, you actually will have only functions of lambda squared. The vertices always come in pairs here. And we'll see this, that it's a function of lambda squared. Okay, so now, I don't know if you've seen a books by Kleinert. He writes these very detailed books on renormalization of 5-4 theory and ON models. If you want to learn exhaustive amounts of information about 4 minus epsilon expansion of ON models, I recommend, for example, this book. and in this book, you can find some pictures of all vacuum graphs in 5-4 theory. This is completely arbitrary. You don't assign any labels, but these are the type of graphs you get in 5-4 theory. And these are the graphs up to G to the 6. You will be immediately, when you look at their scaling, you see that only 4 of these graphs are Milonic. The basic one, then this is a graph with 2 melon insertions, and then there are these 2 graphs, like these 2 kinds of graphs. So only 4 out of 27 graphs, even a lot fewer than planar graphs, okay? And that's the secret for solvability of this theory. And the fraction, so the number of Milonic graphs with p vertices can be shown to grow only as some constant to the pth power, as opposed to factorial growth that we have for the total number of graphs. So it's a very clever limit, but, but it's also very, very restrictive, right? It's still remarkable that such a limit exists, okay? By the way, these are only, I want to stress that these are snail-free graphs. So here I've dropped all the graphs that appear in the vector model, right? In vector, there are additional graphs if you retain snails. Then there will, of course, you can dress up each of these graphs with additional snail insertions. The reason why snails are often not so important in higher dimensional theories because all they do is they just do mass renormalization. So once you renormalize mass appropriately, you can drop all snails, and for example, in 4 dimensions. It's a well-known fact. But if you do plane combinatorics, then in 0 dimensions, then you are supposed to keep the snails. There is no like dimensional regularization that deals with them in a nice way in that case. Okay, so I promised to explain why, how to prove in this case that only melons remain in this theory. And so in this triply colored theory with ON cube symmetry, there is a very simple argument, which it's not a complete argument, but I wanted to flash for you just to give you an idea how the proof works. So in each graph, you want to basically calculate the sum of the number of red loops, green, and blue loops, okay? So how can we calculate this? Well, we can do the following steps. We can first, for example, erase all the blue loops in the graph and just are left with a kind of matrix model graph with red and green loops, or we can do a similar thing for other colors. Now, once you do this, once you erase all the blue loops, then you can actually count the number of red and green loops quite simply in the following way. So we know that this is just the equation for the Euler characteristic that I wrote down before, that f plus v minus e is equal to chi, right? Where f is the number of faces, e is the number of propagators, and v is the number of vertices, right? In this case, also, since each vertex emits for propagator lines, you get that the number of propagators is just twice times the number of vertices in the vacuum graph, right? Because you mark each propagator from each loop, and you get 4v, but then each propagator is marked twice, so you get actually 2v. So then the number of index loops in the red-green graph is just the Euler characteristic of the red-green graph plus 2v minus v. So you get this equation, right? Very simple, right? Just you erase the blue loops, and then you do what you do in the matrix model. Now, do the same thing for the other two ways of erasing. Like, you can do the same for f red-green and f blue-green. If you add them up, right, obviously f red-green is just the number of red plus the number of green loops. So the sum of these will be just twice times the total number of loops, which is what you're interested in. You really want to compute this fb plus fg plus fr. This is obtained by summing these three quantities. But this can be expressed as in terms of the Euler characteristic of blue-green, Euler characteristic of blue-red, and red-green. And then you have plus 3v, right, because each of these had plus v. OK, so then you divide by 2, right, to get this f total. And you get each of these can be written as in terms of the genus. Right? So each chi is 2 minus 2g, so chi over 2 is 1 minus g, right? So that's why we get 1 3 times. We get this factor minus the genus of the blue-green graph minus the genus of blue-red and genus of the red-green. But then, so here comes the crucial thing that, of course, the genus cannot be negative. Right? It's either 0 or positive number. This puts a bound, right? This puts an upper bound on this f total. And the upper bound is saturated if each of these g's is exactly 0. So that's what's called the maximal graph, is when g is 0. So each of these fat subgraphs, double line graphs, will have genus 0. For such a graph, you immediately see that f total is 3 plus 3v over 2, right? But that's exactly the scaling we're shooting for, right? Because n to the f total will be just n cubed. So this graph carries the power n cubed times n times 3v over 2 times g to the v, because it's a graph with v vertices. So this scales as n cubed g n to the 3/2 over v. So this proves, like in 2 lines, that there cannot be anything that scales faster than this, okay? And this proves the existence of the large n limit where lambda is taken of this form. It's not a complete proof because I have not shown that the only graphs that saturate this are melons, but it's a bit, but you can look it up if you're interested. But this already very simply shows that nothing can beat that scaling that I obtained from explicit melon calculations. So that's really a very nice trick. And the power of n that goes with these graphs is often called the Gouraud degree. Basically, it's the Gouraud degree is just what power n goes with. It's what we call this f total. Okay, so this at least should make you feel better that nothing is that basically this melonic large N limit really makes sense, and it's possible to write an explicit computer program that just does the index contractions and computes the explicit functions of N. In this series, actually, my former student Renormalization wrote such a program. And you can grind through all of these graphs, and you see, sure enough, only melons survive if you have any doubts about. So it's quite a beautiful thing. Just to flash one relatively new thing so this O(n) cube theory, for example, how it works has been known for a few years. It was, in the zero-dimensional case, was written down by Carrozza and Tanasa, as I mentioned, and this proof can be given in that case along these lines. But if you go back in history, the original papers only talked about the O(n) group, just a single O(n). And if you have a single O(n), there is no coloring to the graph. You're just going to get 3 strands of the same color. So you cannot really erase anything, right? If you erase one color, you erase the entire graph. So it's much harder. But then, so Tarnopolsky and I wrote a paper where we started studying by brute force what happens in a model where you take a traceless, just take the same tetrahedral interaction with a single O(n) group. So, but now phi ABC is a traceless symmetric tensor. And then we found that in this case too, the only melonic graphs dominate up to a pretty high order. So this is the kind of thing that's, if you're curious, you can see in our paper. In this case, there are 177 diagrams without snails. There is some reason why snails can be erased in this case. But just without snails, you have to evaluate 177 diagrams doing the full combinatorics of delta function contractions. It's certainly not something that's humanly possible. But these numbers here indicate the scaling of the power of N that you get, both in the O(n) cubed theory and in the theory with the traceless symmetric O(n) tensor. And you see that the first 3 graphs are actually, the first 3 of them are in this one also. The ones that's 15 is the right number for g to the 8, right? Because you take out n cubed, you get n to the 12, and that combines with g to the 8 to give the right scaling. And all the rest are suppressed here by at least 1 power of n. So there is vast number of non-melons. Sometimes this traceless symmetric theory is more suppressed than, sometimes the blue ones are O(n) cube theory and the black ones are O(n) theory. Sometimes the O(n) cube is a bit more suppressed than O(n). But this extra enhancement does not cause violation of melonic limit. So we made the conjecture that in this case too, you actually get a melonic limit. And in this case, for example, the propagator has much more complicated index structure. Instead of just one delta function, there are these all these symmetrized terms, and then 6 terms here, and then additional 9 terms to subtract the traces. So it's quite a formidable calculation to do this. You need a supercomputer to do it efficiently, or it needs some tricks. Actually, Fidel Shaposnik told me that he had some tricks which allowed him to check up to g to the 10 that the same thing still works. And more recently, Benedetti, Carrozza, Tanasa, and Klebanov gave a mathematical proof. It's much, much harder than the proof that it relies on doing surgery to graphs. You cannot do this very simple sort of argument. this theory, but it does work. So it gives us confidence that even the models with a single ON can be melonic, which is quite interesting. Okay, so that's a kind of a bit of a survey of the basics of this model. So what we were doing was just pure combinatorics. Just take a bosonic phi ABC tensor and just do combinatorics of these connected graphs. And then we find out some very interesting stuff like this melonic dominance. Now I will switch a bit back to actually doing a bit more formal evaluation of the leading large N limit in these models. And then my plan is in the next lecture tomorrow morning, I will talk about the D=1 models, the quantum mechanics of the fermionic tensor with these symmetries. I want to add one disclaimer that it turns out that of the type of models we're interested in, the one with symmetric tensor, so even though this is really interesting that this works for the bosonic case, but if you turn them into psi's, anti-commuting ones, this is just going to vanish. Because there is a simple, like, vanishes due to Fermi statistics of psi's. For bosons, it's fine. But anytime you have a symmetry or anti-symmetry in a pair of indices, this vanishes. So this is not satisfactory for promoting it to the fermionic model, but it's fine for the bosonic model. So this is basically the story. If there are any questions now, maybe I'll... Okay, if not, let me just talk a little bit about this evaluation of these functions that appear in this case. I almost did it for the case of vector model, and it's, I probably don't have time to do it in complete detail. So what did I do? I wrote down with the help of this Hubbard-Stratonovich trick, the Z vector could be turned into the following integral d sigma from minus infinity exponential of minus 6n sigma squared divided by lambda, and then minus n over 2 log of 1 plus 2i sigma. Okay, this term just came from integrating over phi k, right? This started with, there was a term minus phi k squared over 2 times 1 plus 2i sigma. Okay, you do this Gaussian integral, and then you just pick up this 1 plus 2i sigma to the power of n over 2, right? It's very simple. And then you put it in the exponent and you get this. Now, also people were asking me after class, if you make these phi's anti-commuting, then obviously this determinant is going to go from the denominator to the numerator, and then you reverse the sign of n. So the anti-commuting models like effectively give you negative n. Right, so now we can do the saddle point evaluation, and we see that saddle point comes from an imaginary G. So we get that saddle point at sigma is equal to minus I sigma tilde, where sigma tilde satisfies the following equation, which you just vary from here. You get 12 sigma tilde divided by lambda. is equal to 1 over 1 plus 2 sigma tilde. Right, this term comes from here, and this term comes from here. And this is just a quadratic equation, right? So we know how to solve this. We get that sigma tilde of lambda is equal to, and we pick the branch of the square root that matches correctly onto perturbation theory. We get 1 plus 2 lambda over 3 minus 1 divided by 4. Okay. Right, and then the idea is to look at this. So then log z vector divided by n is equal to f0 vector of lambda plus order 1 over n. And we just plug in the value of the saddle point to this exponent, right? So the contribution will just come from this exponent. So we see that, that in this case, f0 vector is just equal to 6 sigma tilde squared divided by lambda minus 1/2 log of 1 plus 2 sigma tilde, where sigma tilde is given by this equation. Right, so it's a completely explicit solution of the leading large n limit. And when you expand it in lambda, you can see that our knowledge of how to do Feynman graph combinatorics was okay. You indeed get, like, the leading term was minus lambda over 24 plus lambda squared over 144, and so on. Okay. And you can write down the following. You can write down some formula that works to all orders, like this is sum k equal 1 to infinity minus lambda to the k, 1 over 4k, k plus 1, 6 to the k times 2k, k. Okay. So one thing that you immediately notice is that the coefficients actually are decreasing in this series. Like, for example, the next one is 5 lambda cubed divided by 2592. So you don't see this wild factorial growth of that we saw from the evaluation of the leading graph. I mean, of the n equal 1 theory. Okay, and the really interesting thing from here, you see that this expression makes sense even for negative lambda, right? Remember, lambda, we're dealing with a theory where when g is positive, the potential is positive, but when g is negative, the integral, strictly speaking, does not make sense. But this can be analytically continued even for negative lambda. So there is, first of all, the finite radius of convergence. So there is, so this actually converges for absolute value of lambda less than 3/2, right? Because this defines for us the radius of convergence. And for example, for negative lambda, it makes sense for lambda bigger than minus 3/2, but it makes sense. So for example, you can do the expansion. So there is this lambda critical, which is equal to where this branch cut appears here, which is minus 3/2. And you see that f0 of lambda, as lambda approaches lambda critical, we get, this is some constant, like 2 log 2 minus 1 over 4, minus 1/6 lambda minus lambda c, and then plus 2 9s root 2/3 lambda minus lambda c to the 3/2. So this is the first non-analytic term. Right, this fractional power here. Okay, so now in this business of doing these planar graphs, it's very typical that the leading large N limit has a function that can be analytically continued to unstable regime of the problem. So you can say that large N kind of is a stabilizer. You can stabilize things by taking large N limit first. So if N is taken to infinity first, then some unstable potential can become stable in some sense. And this is a very simple example of this. And also, often people associate the leading non-analytic term. There is a definition called the string susceptibility exponent, people call it. So this you can write as lambda minus lambda c to the 2 minus gamma. That's, you can also read in my 1991 notes. This is a common notation. And here you see that this gamma is equal to 1/2. This is actually the most generic value. And this corresponds to, whenever people see this, they usually kind of get disappointed because it is the most generic value. And it's characteristic of polymer-like graphs. This is what people call branched polymers. You get this type of leading singularity in many, many systems, and they tend to be. So here we know that they are polymer-like because there are just chains of bubbles. Okay? So that's a complete solution of that situation. So now let me discuss what happens in the matrix model, because in the matrix model, actually something nicer happens, or a bit different that can happen if you take the single trace interaction. So if you take the matrix model with this single trace interaction and put here G over 12, for example, and then you can just proceed to evaluate the graphs first by brute force and then by more clever method. So again, we start evaluating like this figure 8 graph and the melon graph and triple bubble. And you get the following story. So for the contribution to log Z matrix over n squared, so this graph gives for us minus 1 over 24, 2n plus 1 g. This graph gives like 1 over 288. If you're curious, you can try to reproduce these formula. And if you disagree, send me email. I mean, it's not that important that how the subleading terms work for my purposes, but n squared. Excuse me? Oh, right. Sorry. Yeah, let me. It's hard to disagree with something this small. So. I will post these notes. I will post them today so that, so maybe that gives me an excuse not to write out. But yeah. So log Z matrix for n squared. There is minus 1 over 24, 2n plus 1 g. Right. That's the first graph. Then there is 1 over 288 n squared plus 2n plus 3 times g squared, right? And then there will be like 1 over 144 2n plus 1 squared g squared. And then some order g cubed graphs, which I will not write out. Yeah, I think this is again the contribution of the, this is the melon, and this is the triple bubble. And here you notice explicitly the really remarkable thing that they're of the same order, right? You see explicitly that both scale is n squared times g squared in this leading large n limit. So as advertised, we can then from here read off that F0 of lambda right, so this F0 matrix will be like minus lambda over 12 plus lambda squared over 32. And then if you do the next order, you get minus lambda cubed over 48. So you already see that no big disasters seem to happen with these coefficients either. Like the planar expansion does not have these rapidly growing coefficients. Okay, and you can actually solve this problem exactly too, not through Hubbard-Stratonovich transformation, but there is a standard method of dealing with these matrix models, which is to integrate out the angles and reduce it to the integral of over eigenvalues. So you introduce eigenvalues kappa A of this matrix, and then Z will be a product over A, integral d kappa A. And then there is a square of the van der Monde determinant, delta squared of kappa, and then just e to the minus sum over 1/2 kappa b squared plus g over 24 kappa b to the 4. Sum over b from 1 to n. And this is a famous van der Monde determinant. Delta is product of kappa A minus kappa B. Product over all pairs, right? Sorry, product. Okay, so now what you can do to get the leading large n limit is to introduce the density of eigenvalues, because the eigenvalues will just get bunched up. So there is this, when g is 0, you get this famous Wigner semicircle law. And then it gets deformed by this potential. So this is the problem that was beautifully solved in this historic paper by Brezin, Itzikson, Parisi, Zuber. They basically figured out how to introduce, so they introduced density, eigenvalue density, which is rho of k. Basically, when there a large number of eigenvalues are packed into a small region, you can approximate this just by a smooth function. And then they wrote down an singular integral equation that describes it. And the solution for eigenvalue density is remarkably simple. Like you introduce a quantity a squared of lambda, which is square root of 1 plus 2 lambda minus 1 over lambda. It's a bit similar to the quantity that I had also in the vector model case, also has a square root, right? And then rho of k of kappa is found to be 1 over pi, 1/2 plus lambda over 6 a squared plus lambda over 12 kappa squared square root of 4a squared minus kappa squared. Okay, so you see that when lambda goes to as lambda goes to 0, lambda goes to 0, a goes to 1. Right, just from here, a will go to 1. And then you get just this eigenvalue density distribution will be just this semicircle law, will be just this function of square root for a squared minus kappa squared with some normalization factors. You just get this thing. Okay, and then once you include interactions, they tend to sort of start changing these edges of the distribution. And then you can get some critical behavior. So the critical behavior happens again at negative lambda. Remember that lambda here is Gn again. So the potential is positive definite when G is positive. But again, you can continue the story to negative lambda. In this case, you find that lambda critical, so let me, so you get that lambda critical is just exactly where the branch cut develops here, which is minus 1/2. So lambda critical is minus 1/2. And you can express, when you plug in this row of k and do the integral, you find the following expression for F0 matrix. That's equal to 1 over 24, a squared minus 1, 9 minus a squared. And again, there is a logarithmic term, minus 1/2 log a squared. This, the expansion of this indeed matches onto this perturbation theory. You can reproduce the first few orders. But then here's the remarkable thing, that this F0, as lambda goes to lambda critical, you find that F0 does something like this. F0 will be a plus b lambda minus lambda c plus c lambda minus lambda c squared. And finally, you get a term of order lambda minus lambda c to the 5/2. So you see that the singular term appears not like in the 3/2 position here, but in the 5/2 position. So you see that this is characteristic of actually good planar graphs. It's characteristic not of these polymer-like graphs, but planar graphs. So here you see that gamma is equal to minus 1/2. And this is in exact agreement with Liouville theory. So this was one of the early triumphs of this matrix model approach. There is this Knizhnik-Polyakov-Zamolodchikov approach to computing gamma scaling, and this agrees with so-called KPZ, and then David Dissler and Kawai did it more in a different language, this KPZ-DDK scaling. Okay, so here we're clearly getting something different characteristic of these planar surfaces. And then finally, I'm not sure I'll finish it today, but at least I'll start. The punchline will be what happens for these tensor models. Okay, so for tensor models, I already showed what the basic setup is. Let me just do the ON cube tensor model. Oh, I'm already late. Oh, okay. Yeah, let me just, sorry, I somehow got mistaken. Yeah, I will just stop here and then do quickly the But I will submit the notes so you can see the discussion of the way the tensor model is solved is by means of a Schwinger-Dyson type resummation equation. So each time there is a different trick. First there was this Hubbard-Stratonovich, and then there is this eigenvalue density, and then there is another trick for the tensor model, but it gives something rather similar looking. Okay, thank you.